Where does material science come into play with this project?
Everywhere.
Everywhere.
Everywhere. My name is Steve Thibault. I'm the Chief Engineer at the Space Exploration Sector here at Johns Hopkins University Applied Physics Laboratory. So as a Chief Engineer, I have engineering oversight of all the developments and operations that are occurring here to ensure that we have high quality missions that exceed our sponsors' expectations, that we solve the technical challenges that we have to develop those spacecraft and instruments, as well as to ultimately deliver hardware and systems and software that are working in space. So spacecraft integration and test is where actually all the pieces come together and they get assembled. So we're integrating the propulsion system, the structure, the thermal protection system, the avionics, the computers, the radios, the instruments, the solar arrays, the batteries. We're all putting that into what looks like the spacecraft, running that through a series of tests. So I had a role in guiding the organization to get through the challenges of that integration and test, such that we knew that we had a spacecraft that would succeed in orbit. As you can imagine, when you look at something from afar, you can only learn so much, you can only see so much. And so standing here on Earth, we have all sorts of great sensors that study the sun. We have actually spacecraft in orbit that are at the same distance from the sun that the Earth is, and they rotate around the sun and they looked at the sun, and so they provide us immense science. But nobody has gone close enough to understand the coronal region, which is where these activities occur and take place. And so there's fundamental science that Solar Probe spacecraft is after, both in the electromagnetic domain, but also in the visual. There's a camera on board that actually looks for streaks and actually dust and particles coming off the sun. There's high energy and low energy particle instruments, all to aid us in understanding the physical model behind how the sun behaves, targeted towards how does it impact the Earth. So it's essentially important science. And as an engineer, it's pretty exciting to be able to work on a spacecraft that actually enables discovery science. So I have a very vivid memory that my mother collecting me and my two brothers to sit in front of the television when Neil Armstrong landed on the moon. So I can remember that very vividly, seeing this individual in the spacesuit take these steps down the ladder and actually then touch on something that we could go walk outside and go look and see the moon. And that was very important in my thought process through my education. I always resonated with math and sciences, but I like looking out into space, looking to stars. With a full moon at night, I grab my amateur telescope and I put it out on the sidewalk and I look to just keep my excitement alive about being able to see things that I'm able to do things with. In fact, coming to APL, one of the first projects I worked on was called Mini-RF, miniaturized radar, and it was on the Lunar Reconnaissance Orbiter, which had one principal objective, which was to map the landing sites of where the Apollo astronauts landed, which was pretty cool. But the instrument that we developed was to look for ice in the poles, in the deep permanently shadowed craters. And so this particular instrument actually helped discover ice on the moon, which is just super exciting. So the missions and the contributions you're able to make in the space industry, whether it be on the commercial, terrestrial side or exploration side, are just really exciting.